Welcome. My name is Brian Plummer. I work for the New York Times. Today I'm going to be talking to you about data loading in one of our open source libraries store. A couple of caveats for this talk. I didn't realize I was giving this talk until yesterday evening, and this is a talk I gave at droidCon Berlin a few weeks ago, and I haven't changed the slides, so they're a little bit Germany focused, so you guys might see that. All right, so let's start. So the name of the presentation is Data Loading Made Easy-ish, something we'd all appreciate. We love making apps at the New York Times. We have a couple of apps. We do hack days. We make apps prototypes. We love making apps, as I'm sure most everyone in here does as well. And we love open source, as I'm sure everyone else in here does as well. And why do we love open source? Well, it makes our life a lot easier. I don't know if you guys remember, but before we had some of these awesome networking libraries, we would have to use HTTP URL connection and do a lot of the stuff by hand. It wasn't fun. And the same goes for storage. You know, it's really developed and come along here recently. There's a lot of good solutions, SQLite, Realm, Firebase, Room. There's a lot of alternatives besides plain SQL or shared preferences. Yuck. And the same goes with parsing. We have a lot of good libraries nowadays, Jackson, JSON, Moshi. We're not having to parse JSON objects by hand. Thank goodness, right? So fetching, persisting, and parsing data has become really, really easy. But what's not easy? Data loading. Everyone does it differently. And when I say data loading, I'm talking about the actual act of getting the data from the server or an external system to the user's screen. Now, who in here, raise your hand if you think the person next to you does this the same way that you do? Right? Okay, yeah. And, loading is complicated, and rotation is a special snowflake. And, we know that we're going to use all these great libraries, but, does my activity, really need to do this? What retains the data? And how are we going to serialize it? There's still a lot of questions. So we built the store to help us with our data loading and to make it really, really simple. So that's great. Well, what were our goals? Why did we do it, and what did we set out to do? Well, we thought data should survive configuration change. It should be agnostic where it comes from or how it's needed. Activities should do activity things, presenters should do presenter things, and the presenter should stop retaining lots and lots of data. An offline has a configuration, caching as a standard, not an exception. We want to build this to where it should work offline and be cached correctly. The API should be simple enough for an intern to use, yet robust enough to really fulfill our needs. Our team gets bigger every summer by about 50%. We get about 3 interns, and so we have to explain some of the constructs to them, and we wanted something really easy that an intern can get. Well, how do we work with data at the New York Times? We deal with a lot of data. So we decided to look at the 80% case. 80% of the time, we want data. We want to show it to the user. We don't care where it comes from. We don't care if it's fresh or cached. If we have it, we want to show it to the user. The other 20% of the time is for fresh data. The user initiates a pull to refresh, or we have a background service. Currently, our app has 2 alarms, like a morning and an evening, and we want to actually fetch fresh data during those times. The requests need to be asynchronous and reactive. We use RxJava, so we expect a lot of our utilities to be RxJava compliant, I guess. And data should be dependent on each other, and data loading should be too. Anytime we fetch an article, for example, whenever we fetch an article, we typically want to get the comment metadata as well. So there's this data dependency that we also want to support. And of course, performance is important. We don't want to make extra calls. We want to hook into in-flight responses. We don't want to be doing extra work. If you have 20 similar or 20 identical requests, then we shouldn't be hitting the network 20 times or hitting the disk 20 times. It should really conform to a thunder and herd type of pattern. And the parsing should be done efficiently and minimally as well. Parse once, cache the results for future calls. If we want, or if we make a request for a particular type of data set, let's say data set A, and then later we want that same data set, it should already be hydrated, it should already be in memory. So let's use the repository pattern. And we do this creating reactive and persistent data stores. And well, what is the repository pattern? It's a mechanism that separates the logic that retrieves the data, and maps it to the view model from the logic that actually shows the data. I'll say that again. It separates the data that retrieves and maps it to your model from the data that actually shows the data, from the view that actually shows the data. So sorry. And why repository? Well, it maximizes the amount of code that can be tested. As mentioned, if you really isolate your business logic, and then you can test it in isolation, you don't have to test all the other things, how to get the data, so on and so forth. And one of the other benefits of it is we can get data from different locations, and the end user, the person using the repository, shouldn't really care about where that data comes from. At the end of the day, it just wants the data. And again, here's our implementation of it. Maybe you'll see it one more time, the URL. So, well, what is this store? It's a class that manages the fetching, the parsing, and the storage of a specific data model. You tell the store what to fetch, where to cache, and how to parse it. And the store handles the rest of the flow for you. Stores are observable. We have a get, a fetch, a stream, and a clear, and you can see the all observable interfaces and generics. So let's see how they helped us achieve our goal by loading a currywurst. Again, back with the Germany thing. The Germans love currywurst. So let's load a currywurst. Well, so for the 80% of the case, we just want data. We don't care if it's cached or fresh. We can use a get. So here in this situation, we're saying store.get, we're passing ketchup as a key. And again, we don't care if it's on disk or if it's going to the network. We just want the currywurst. And on configuration changes, all you really have to do is serialize the key. So the key in the previous example was ketchup. You serialize that, and then after the rotation is done, you pull the key out and you fetch the data. You don't have to serialize currywurst, you don't have to serialize your data sets, or anything crazy like that. And well, what do we gain from that? Fragments, presenters don't need to be retained. You don't get the transaction too large exceptions of shoving all that data in the bundle, which you shouldn't be doing. And only the keys really need to be parsable. And as I mentioned before, this thunder and herd pattern, everything should be kind of efficient. If you spin up a loop and you make 20 requests, there should not be 20 separate requests going to the disk or going to the network. It should all kind of resolve down to one. So, fetching new data. As I mentioned, the 80% case, we don't care where it comes from. The 20% case, we want fresh data. The user initiates a pull to refresh. We're in a background update. And the difference is, instead of a get, we use a fetch here. And this forces us to go to the network. This says, I want fresh data. Give it to me. And I apologize, this is a horrible graph, but it kind of explains the flow through, and you can see it's kind of unidirectional here. We check to see if it's in the memory. If it's not in memory, we go and we fetch it, we persist it to the local memory cache, and then we return it to the users. And that's great. We also support stream listens for events. So if you're interested in hearing about updates for a particular data set, we also support a .stream. So anytime anyone gets this currywurst or does a get on it, then we'll also get the value as well here. So let's run through a little example of how do we build a store. And we do it by implementing interfaces. We have, as I mentioned before, you define how you fetch the data, you define how you persist the data, and you define how you parse the data. And all you have to do is implement these constructs using these interfaces. So for example, here's a fetcher. And you can see it's just a basic retrofit endpoint, currywurst API. We pass in our key, which is the topping. As you remember previously, that was the ketchup. And that's our fetcher. Really simple. It can be as complicated as you want, depending upon how you fetch your data. Ooh. There we go. All right, so sorry about that. And if you don't use RxJava, then a simple little pattern like this, where you can say observable from callable, will cause your your networking, or for in this example, your retrofit API to be observable. And as I mentioned earlier, parsers. Well, parsers help translating your data, because a lot of times the data we get back from these endpoints isn't really in the shape or the form that we want to pass up to the UI layer, and that's where the parsing comes in. There's a nice gives us the ability to translate the data. And the same here. So as mentioned, you just have to implement the interface. So here we are taking a currywurst and putting it in a box for maybe a delivery. And this shows you, it's a really basic example. We're just wrapping the currywurst in a currywurst box. And this is a very simplistic parser example. And others, you can also use read streams. You don't have to deal with objects completely. Here in this example, we're reading from an input stream, and we're using JSON, so on and so forth. And we support other middlewares too. It doesn't have to be JSON. It could be Jackson or Moshi or whoever. We support them all. Oh, one more horrible flow graph. So this is the way it looks like with parsers in the mix too. And you can see there's one extra step before we save it into the memory cache. We perform the parsing and then do that. So that way later, if you request for like data set A, then we've already done the parsing, we've already done the hydration. It's there in the memory, ready for you to be used. And I mentioned earlier about offline persistence. How do we do that? Because certainly we want this store to work offline. And as I mentioned before, it's about implementing an interface. One of the ones that we have built in is a file system record persister. You can use your own. Well, I'll get to that. But here's an example of that. We have a currywurst plus the key, and we can specify the caching policy. How long will it live on disk before it becomes stale? And it's keep it simple, stupid storage. We have these basic methods that are implemented, and we provide it as a module if you wanted to use it. You know, and if you don't use it, you can certainly write your own. It doesn't have to be file system. It could be Realm. It could be SQLite, SQLite. It could be any other type of storage, room, so on and so forth. And again, this is what you would have to implement if you wanted to write your own. Basically, we have an ability method for read based off a key and write as well to clear it, and some record state information. This is the last one, I think. So this is what it looks like with the persister in the mix. And you can see it's a nice unidirectional flow. We ask ourselves, is it in memory? No, it's not in memory. Is it in disk? No, it's not on disk. Let's go to the network. Let's persist it to disk. Let's parse it, put it in the memory cache, and then resolve the request. So let's build a store. Now that we've talked about all the different pieces, let's put it together. But real quick, I just want to point out that we support multi-parsers. So if you had a chain of parsers that you wanted to do and you didn't want to have everything in one parser, it supports it, and it does it by order. So it would hit the first JSON parser, and then it would hit the box parser, as we showed earlier in the slides. So here we go. See the declaration. We declare our store. We declare, firstly, the key that we use, what we get from the fetcher, the buffered source, and then the item that we actually get out of the process. And that's what's actually going to be returned from the parser, the end result of the store. So here we declare our fetcher. It takes the topping, and it calls currywurst source, which you can imagine was probably a retrofit endpoint. The persister, just like I showed you in the previous example, we're using our file system record persister here with a one-day caching policy. And there we attach the parsers that I've declared at the top. And that's it. You say .open, and you have a store. So let's configure the caches. I mentioned there's caching that it supports. We do memory caching here, so you can set the memory caching policy, size, expire after, and you can specify the units. And in addition to that, we can also do refresh on stale, backfilling the cache, and it's just an additional command right here, refresh on stale. All right. And we also do network before stale policy as well. It's very similar. It's another line item right there. All right, so let's check out an example of a store. And this is actually something our interns implemented maybe 2 summers back. The New York Times, we have a list of best sellers. And this was a new feature where we were going to show a screen showing the list of bestsellers, and not only that, but it also had to support this notion of categories as well. And our interns did this, they picked it up, no problem. And so what they did was, here is the actual retrofit endpoint You see it's pretty straightforward. We specify a category, hardcover fiction, hardcover nonfiction, those types of things. And then they wrapped it just previously, just like I showed you. There they define the fetcher. They use the file system for the persister, and the create source parser for the parsing part, which uses JSON to actually hydrate the objects. And that's it. And in the activity, it could be something as simple as this: bookstore.get.subscribe. Of course, you'd want to hold on to your subscriptions, if you're using RxJava in this situation. But it's really that simple. And if we wanted a fresh copy of the data, we do a .fetch. And again, this is either a user-initiated pull to refresh or a background update. And the data is available when the screen needs it. UI calls get, background services call fresh. As I've mentioned, that's how you do it. And it also works with live data. Live data is no problem. There's a couple different ways to do live data, and both ways work. You can embed the call to the store within the live data in your onActive method, just like you would here. And I want to say on the deactive method, you would just clean up your subscription. And the same goes for an external setting of the live data. Here you can see where we say currywurst store.get, and on the successful emission of the result here, we actually set the live data object. So it works with live data. Dependent calls. Sometimes we have data sets that are dependent upon each other, and we need to map one data set to another data set. And so here's an example of it, where we get the section front. So here's an example of where we specify a section, and we want to get additional information. Here we have what's called a feed.getSectionMeta. And so you can see here we're getting additional data. Oh, I'm so sorry. Again, I apologize. So here you can see, I'm drowning on this. We're kind of chaining two stores together. We have a feed store.get, and when we get the meta information about a section front, that's passed down, and you can see a section front store.get. So we can chain stores together to make the data calls dependent upon each other. You can also override the get and the fetch. You can extend the store yourself and override it yourself. So here's an example. We have a video store which returns single videos, playlist. Video store returns single videos, playlist. Store returns playlist. How do we get a playlist of all the videos? All right, so step one, we create a video store. And next, we create a playlist store. Again, I'm so sorry, apologizing. It's been a couple of weeks since I've given this talk. It's a little out of my mind. I'm making Mike squirm right here, I bet. So here we go. So this is the real meat of it. Video playlist store, we extend the real store, we override the get functionality, and we have some business logic contained therein. So we want to do some additional things outside of the store. You would also have to override the fetch method as well, because we have a get and the fetch. The get is for stale data or data that we don't care where it comes from, and the fetch, of course, is the fresh data. And you can see here where we have business logic that actually transforms it before it's returned externally. All right, so how do we listen for changes? We are subscribing for things. How do we listen for a particular data set that we're interested in when it changes? Well, as I mentioned, we support this .stream operator. And you can listen and do a .filter, because it's a reactive stream, and really only look for changes that interest you. If you're showing a particular data set A, you can listen for just A and then react to how it changes. Store 3, we just recently rolled this out a few months back. There's some new features. If you guys have used Store before, then these are some new features that come with it. This one is one of the features we added was get refreshing. It's very similar to get, but you stay subscribed, and whenever that data is cleared, anyone who's listening with this get refreshing will kick off a network request and then get the updated data. And there's also get with result, and that basically returns to you additional information about your data set, about where it came from. Did it come from the disk? Did it come from memory? So that way, if you wanted to do something a little different, depending upon where that data came from. And yes, we do Kotlin. One of our modules supports Kotlin, and you're able to build a store using Kotlin. And here's some examples of a fetcher, and then the very bottom, the actual building a store. And that's it. Would love contributions, would love feedback, anything that interests you. We would like to hear about it. If you don't like it, you check it out and you don't like it, we'd love to hear why. If you use it and love it, we'd love to know that too. Or if there's a feature or something you would like, we'd love to hear that as well. We're pretty good about responding to people's requests. So thank you, and questions.